All right, welcome to the explainer. Inside every massive machine, every spinning turbine, there's a hero that nobody ever talks about. We're talking about a component that literally carries our modern world, and it is locked in a constant, brutal fight against the laws of physics.
So what are we even talking about here? It's not some flashy new AI chip or a roaring engine. No. It's something much more fundamental, tucked away, hidden from view, doing probably the toughest job in almost every piece of tech we rely on.
Yep, it's the mechanical bearing. And here's the crazy thing. Once you know what you're looking for, you start seeing them everywhere. But behind that simple idea is this relentless onslaught of physical forces, which makes designing them and just keeping them alive a constant, high-stakes engineering puzzle. To really wrap our heads around why this is such a puzzle, we've got to zoom way in, right down to where it all begins, the drawing board. We're about to enter the microscopic world, where even the tiniest, simplest assumptions can lead to catastrophic failure. Okay, so it all kicks off with this one core idea, load distribution. On paper, it's this beautiful, clean concept. A bearing takes a massive force and just spreads it out perfectly, evenly, across all its little rollers or balls. It's a neat calculation, but you know where this is going, right? The real world is never that simple. And this is where it gets really interesting. This slide just lays it all out, the massive gap between theory and what actually happens. Our simple models, they give us one number. But when we run these super powerful computer simulations that actually account for the tiny, real-world flex of the parts around it, boom. The load on the most stressed roller suddenly jumps by 15%. I mean, that's not a rounding error. That's a huge deal that can throw an entire design into question. So what does this all mean? It means that before a bearing even does a single turn, it's already a minefield of engineering compromises. Tiny microscopic errors from machining can concentrate the load in one dangerous spot. The exact shape of a roller might be great for strength, but maybe it's terrible for how lubricant flows over it. And even when you preload them to make a system stiffer, well, that just throws a whole new wrench into the works with a bunch of internal forces you can't even predict. All right, so that's the design. But let's move on because this is where the real battle begins. We're talking about a constant, microscopic war against friction. And this isn't just about being efficient. This is a fight against heat, against wear, and against spectacular failure. The only thing standing between a perfectly smooth operation and complete, catastrophic failure is this tiny, microns-thick film of lubricant. It's literally the bearing's lifeblood. But this lifeblood is so fragile. A single speck of dust, a sudden spike in temperature, even the friction inside the oil itself can cause that whole protective film to just collapse. So, what happens when that microscopic shield is gone? What happens when that battle is lost? Well, the results are fast, and they are not pretty. And wow, this slide really shows you the brutal aftermath. Without lubrication, the metal surfaces just start tearing each other apart. You get something called spalling. That's where the surface just cracks and shatters like a neglected old road. You get flaking, where chunks just break off, and then there's smearing. That's where the heat gets so intense it literally welds the surfaces together for a split second before they're ripped apart again. It is game over. Okay, so we've been deep in the microscopic weeds. Let's zoom way out now to the macro world. How on earth do these super sensitive parts actually survive in some of the most punishing environments you can possibly imagine? And believe me, this is where things get really tough. Pretty much every application is its own special kind of nightmare for a bearing. For a wind turbine, you've got unpredictable winds and this really weird failure called white etching cracks that, get this, scientists still don't fully understand. In a jet engine, it's so hot you can't even use oil. You have to rely on solid lubricants. And for things like high-speed trains or deep-sea oil rigs, the real challenge is just trying to hear that bearing cry for help before it's way too late. Just look at this number for a second. In heavy industrial gearboxes, engineers have literally watched bearing temperatures jump from a stable 80 degrees Celsius to over 100 degrees in just a few minutes. That's not just getting a little warm. That is a full-blown, hit-the-emergency-stop kind of situation that risks a total seizure. Oh, and the list of operational nightmares? It just keeps on going. At really high speeds, rollers can start to skid instead of roll, basically grinding themselves away. If a load is just a little bit off-center, the rollers can twist or skew, and that creates these incredibly dangerous temperature spikes. And in the real world, perfect alignment is basically a fantasy, which means you've always got damaging stress focused right on the edges of the rollers. So, because failure is so catastrophic and, let's be honest, incredibly expensive, the holy grail here is predicting it. But trying to detect the faint whisper of a tiny failing part inside a massive roaring machine, well, that's one of the biggest challenges in data science. It's like trying to hear a pin drop in the middle of a rock concert. It's a race to find that one signal in an ocean of noise.
And this is exactly why it's so ridiculously hard. First, you gotta gather all this data, vibrations, sounds, everything. But then comes the part that feels almost impossible. You have to filter out all the thunderous noise from the motors, the gears, the housing, everything else that's screaming at you. Then you need an expert who knows the exact subtle frequency to look for. And even if you find it, the signals are so complex that it's super easy to get it wrong. Of course, we're throwing AI at this problem, but we're running into a classic dilemma. On one hand, you've got your data-driven AI. It's great until you show it something new, a situation it wasn't trained on. Then it just kind of falls apart. So you try a physics-based model, but that's only as good as our equations. And as we saw at the very beginning, our equations are, well, just not good enough to capture the messy reality of what's actually happening. And this isn't just a theoretical problem. This has huge, real-world consequences. Take high-speed rail. The systems we have by the tracks are pretty good at catching a bearing that's already screaming in pain, but they're terrible at catching that tiny defect right at the beginning. The bottom line is our monitoring is always playing catch-up, which means we find problems when they're already expensive and dangerous. So, when you step back and look at the whole picture, what you see is this incredible story that scales from the absolutely invisible to the unimaginably massive. Think about that. One microscopic design choice, one tiny flaw in a roller, can create a ripple effect that ends up threatening a billion-dollar wind farm or grounding an entire fleet of aircraft. And that really brings us to the big final question, doesn't it? Our ambition to build faster, hotter, more powerful machines is constantly pushing the limits. But that ambition is always going to be chained to our ability to solve these tiny fundamental challenges. So the question is, as our technology screams into the future, can the engineering of this tiny, unsung hero possibly keep up?